Good morning, everyone. My name is Juneyoung from CryptoLab, and I'm going to give a talk about prototyping a compiler for homomorphic encryption in MLIR. First of all, let me describe what homomorphic encryption is. In homomorphic encryption, the encryption scheme allows you to perform certain operations on the encrypted data. For example, after your private information is encrypted into ciphertext, you can perform addition, multiplication, and ReLU, and so on. This means that now the security indeed makes the private AI fully safe. In information theory, there are three states of data. The first one is the data at rest, and the second one is in transit, and the third one is in use. And the homomorphic encryption is indeed the security for the data in use. On the market, there are primarily two kinds of libraries that are, being sold. The first one is a library for homomorphic encryption, which provides core homomorphic encryption operations. This includes CryptoLab's Heian and Microsoft Seal and Duality Technologies Palisade, and etc. The second class of libraries is the application layer, which implements machine learning and many statistic operations using homomorphic encryption. The usage of homomorphic encryption is being increased rapidly, but currently there are a few very important challenges, and I'd like to briefly introduce those. The first one is that the ciphertext is large. In order to represent how much it is becoming big, I'm going to briefly introduce a simple homomorphic encryption scheme. Before everything is encrypted, the plain text, or we say the message, is just a simple array of double. After encoding, it is first transformed into a polynomial, which consists of integer coefficients. Here, it is the integer coefficients that contain the data. And then on the plain text, encryption is done, and a pair of integer polynomial is created. In this integer polynomial, the data of plain text is properly hidden under random polynomials, and you cannot easily recover it because it is known to be a hard mathematical problem. Now, let me briefly talk about this integer polynomial a bit more. Integer polynomial is, a polynomial with large integer coefficients, but the integer is indeed large. It is like 2 to 1,800, so we cannot deal with it efficiently if it is naively used. In order to address this, we use Chinese remainder theorem. We carefully pick a few prime numbers and then present the big number using the remainder on the prime numbers. Therefore, the integer polynomial can be represented as a two-dimensional array, where the size of the first dimension L is the number of prime numbers, and the second number n is the degree of the polynomial. Usually, the n and L is chosen pretty large, so that the degree of the polynomial can increase up to 2 to 17, and also the number of prime numbers can increase up to 30. Therefore, if the packing is done efficiently so that the size of the message, which is n, is equivalent to the degree of the polynomial, at least the factor of L is multiplied. And after encrypting into the ciphertext, 2 is multiplied again. Therefore, you can see that even if the message is optimally encrypted into ciphertext, about 60 times of the size is increased. The second challenge is that polynomial operations are expensive. In order to show this, I'm going to concentrate on the convergence between plain text and ciphertext, which will be encryption and decryption. In order to do encryption, we are going to choose a secret key, which will be an integer polynomial. Then, encryption is done as follows. Given a plain text P, which is another integer polynomial, Ciphertext, since ciphertext is a pair of integer polynomial, it consists of two elements. The first element is a freshly chosen random polynomial, and the second element is some expression on the polynomials with fresh error, small error added, which is described as plus e. And then we can define decryption as follows. Decryption takes a ciphertext, which is a pair of poly, and using the secret key, it recovers the approximated value of the polynomial by properly adding the two elements with s multiplied. You can see that the return value of decryption is p plus e, not p. This implies that homomorphic encryption schemes, in this case, is approximated. Okay, then let's look into the two operations that we used while doing encryption. First, adding two polynomials is done here, and it is described as a two-dimensional loop. Well, in this case, it is actually fine because the constant that is multiplied to the operation compared to the operation on the message is not very high. Well, it is L, but at least it is just L. It contains one modulus, and it is known that doing modulus operation is expensive, but there are a few solutions. However, doing multiplication on two polynomials is slow because the night product requires n-squared time complexity. Fortunately, there is also a solution which is analogous to using the discrete Fourier transform in the modulus, but it is still slower than simple Hadamard multiplication on the message because it requires running the discrete Fourier transform operation. And what is further challenging is that homomorphic encryption tends to be run for diverse environments. First, homomorphic encryption is beneficial to run on-premise because if you run the algorithm on your local machine, then you do not need to encrypt whole data. At least for your local data, you can just use the raw data. Furthermore, the encryption and decryption operation must be done on premise because you cannot export your sensitive private data to other and run encryption on the machine. And secondly, utilizing both GPUs and CPUs brings high benefits in the case of homomorphic encryption. GPUs are fast, but it is less cost-effective than running casual deep learning application because we do not use floating point operations. Also, high-end server CPUs recently have many cores, and they are pretty good at integer benchmarks, so it is beneficial to utilize them. Also, ciphertexts are large, so sending them to GPU is expensive in terms of memory bandwidth. And what is further, pre-calculated keys that are used by useful operations such as cyclic rotations are even larger than ciphertext. So it is just good to run things on CPUs rather than sending them to GPU and run them. In order to address this concern, what I did recently in CryptoLab is to prototype a compiler for homomorphic encryption using MLIR. It is named Heian.MLIR, and here Heian is the name of the product for homomorphic encryption library in CryptoLab. It takes the source language, which is called Poly. It is a new language for high-level operations on polynomials. And then the Heian.MLIR converts the polynomial operations into efficient machine code. Currently, it is in a developing stage, and it is being prototyped using MLIR. But it already can generate fast code for decryption and decoding, which is very important for users because sometimes homomorphic encryption operation itself is shorter than simply performing the encryption and decryption. And also, it can generate code for cyclic rotation, which is just shifting the elements of the message by some given amount. Rotation operation is very important in homomorphic encryption world because it is heavily used for example, doing matrix multiplication. Also, it currently provides OpenMP offloading and in primitive cases, it supports CUDA offloading as well. Now I'll briefly introduce how the Poly language looks like. This is a simple sample code that that describes how encryption works. First of all, you can see that there is an attribute at module which describes which homomorphic encryption parameter we should use. In this case, it is named FBA, which defines the set of prime moduli and what is the degree of polynomial and etc. And you can see that there are two arguments for this encryption function, and both of those are having poly underbar entity type. It means that they are polynomials with entity conversion already applied. Here, entity is a shortcut for numeric, what is it? Well, it is numeric transform something, and it is analogous to the discrete Fourier transformation in this integer world. And you can see that the int max is described as the dimension size. It means that it is maximally using the prime moduli that is provided by this HE parameter. And you can see that also there is this poly type which does not have entity applied. And then now here is some random sampling operations, and also there are some operations on polynomials. And for slightly more complex operations like cyclic rotation, we provide more types and operations. For example, we use an array of entity converted polynomials, and also we can load a predefined constant and expand some custom macro that are defined for homomorphic encryption and etc. And also, yeah, we can create a poly array. Then how are they lowered into the machine code? First of all, polynomials are lowered into tensors, and the conversion is pretty straightforward because we can simply use the tensor type in MLIR with the I64 type. One interesting thing about lowering polynomial is that in homomorphic encryption words, the dynamically shaped tensors are mainly used. The reason is that there are operations that change the prime modules that are used for polynomials, and then after this, the size of the polynomial should change. Therefore, most operations in homomorphic encryption must take polynomials with dynamically shaped form. Also, for polynomial array, we are simply using the three-dimensional tensor, and I think it worked quite well. And for messages that are currently presented as tensor of one-dimensional complex. For bufferization, we used comprehensive module bufferization. Since polynomials are large in this world, minimizing buffer allocation is very important. And MLIR's comprehensive module bufferization exactly fits for this goal, so we use this transformation. However, there are a few challenges in using this path. The first one is that it works well when called functions have their bodies, which means that we cannot simply call some unknown functions. And also, it does not recognize functions that fully overrides the given buffer. In that case, it simply allocates, it tries to allocate a new buffer without reusing the existing one. Also, the transformation cannot, sometimes it doesn't work well for nested linear generic loops or function calls inside loops. So I had to find a workaround for this case. Well, what I've thought during addressing this concern was that I guess someone already has same experience with this, and it would have been great if we could share experience about comprehensive module bufferization. Also, if anyone needs help in using this path, I'm willing to help provide my experience. When MLIR didn't work well for homomorphic encryption, there were two cases. The first one is the usage of tiled tensors. In homomorphic encryption, using tiled tensor operation is useful because for each row of polynomials, we can individually apply operations. For example, in the case of applying forward entity, we can individually apply each row of the polynomial, and then it is equivalent to simply applying forward entity on the full polynomial. However, the denied that tiled loop had been deleted from MLIR. So this had been a bit bad news for us. Fortunately, we could find the workarounds for supporting this, but I think that it would be great if tiled loop can be supported more better in the MLIR world. The second one is about affine loops iteration spec check. There are a few operations in homomorphic encryptions that have loop bounds of shift operation form. And since affine loops does not accept the form in some cases, we couldn't simply use the many useful optimizations on affine, such as affine scarlet. However, still using MLIR was a great experience for prototyping the compiler. And I'm going to describe in which case it could bring performance benefit. I found that loop fusion is very helpful in collecting low-hanging fruits. On the left code, you can see that there are two codes. The first loop is a nested loop working on array A and storing the result in B. And the second loop is working on array B and storing the results into C. If the two for loops are individually parallelized, then there must be the synchronization barrier between these two. After loop fusion, we can see three benefits. The first one is that the size of the working sets are reduced by L because the inner for loop now works on the fly. And the second one is that it facilitates memory optimizations because, for example, in this case, you can see that the location B is dead, so it could be removed. And this is important because in the case of HE, buffers are pretty large. The third benefit was that, as you can see, the synchronization points of OpenMP offloaded loops is removed. And this was pretty helpful in improving performance for multi-core operations. In MLIR, we implemented various algorithms. We implemented number theoretic operations such as for the backward entity and Frobenius map. We also implemented several modulus operations that are also used by other cryptography libraries as well, which are Barrett reduction and dot product with modulus. We implemented sampling, and also we implemented for the backward best Fourier transform, but with slightly different solution order because the list of solutions that is used for homomorphic encryption is slightly different. So far, I've described about the Heian.MLIR compiler, and I'm going to briefly introduce the experimental result. The competitor is Heian, which is the library that I introduced just before. It internally uses Intel HEXL to boost the performance of homomorphic encryption operations, especially for AVX512. I used 3 machines. First 2 are Ryzen. Well, it does not provide AVX512, but the HEXL still provides efficient operations for AVX2. So using HEXL has meaning. And the third machine is Intel Xeon Gold, which provides AVX512. For the number of cores, I used 1 as well as the full cores. And for the benchmarks, I used encode and encrypt as well as decrypt and decode. These loops are primarily goals at the moment because, well, they must run fast on very diverse machines. Also, we are currently trying to fully support cyclic rotations in the close future. And this is the experimental result. For the single core results, I found that, well, performance benefit was not very clear, especially in the case of the third machine, which has AVX512. The Intel HEXL got very high benefit. But when it comes to multi-core, we found that the parallelization worked very successfully, and we could get about 40% speed ups. Also, for other operations such as encode, encrypt, and decrypt, we could find a similar trend. For single core, the performance trend benefit was not clear, but for multi-core, it got consistent speed up. So far, I introduced the experimental results, And here is the discussion and future works about developing the compiler. The first one is about correctness of compilation, which is what I'm also very interested about. In homomorphic encryption, preserving the distribution of randomness is very important for security. But it is not trivial to check whether the distribution is correctly preserved into the machine code. And in order to check this, I believe more than testing approach is necessary. The second one is about the basic modular operations for cryptography. Many cryptography libraries use similar operations, especially in terms of modulus. And it would be great if they could be shared so that developing compilers for cryptography also can benefit from MLIR. In the case of Heian MLIR, we defined it in both Aris dialect individually. This is the end of talk, and I am willing to take any questions.
Great, any questions?
Thank you for the talk. Yeah, I have two questions. The first one is, you mentioned you implemented operators specifically for crypto. Did you implement them in Lineage or this is separate?
Oh, you mean random sampling?
Yeah, I saw some operators for crypto that you had on one slide that you said you implemented them, like modulo, dot product, and some more. Yeah, those ones.
Well, actually, we lowered it into multiple dialects. For simple one, we directly lowered into Lineage. But for some loops that cannot be represented in Lineage.generic, we put some placeholder, which looks like which is a function call to some predefined function signature. And after going down to the later pipeline, we lowered the placeholder function calls into lower level dialects, such as SCF.
Yeah, yes, it was a bit of my second question. I followed up to the Lineage, but I didn't catch the part where you are lowering it to get the results that you showed. Could you talk briefly about how you lowered from the MLIR dialect higher level to actually getting executable code?
Sorry, maybe I did not understand.
How did you, from the Lineage, let's say, representation, how did you get the numbers that you showed? What is the lowering that you applied to them? Or maybe no lowering was required? And yeah, I'm just curious. It's okay if the question is a bit complicated, we can take it offline.
Yes, maybe we can talk offline.
That's all right, yeah, thank you.
Thank you for your talk. You had some numbers where you mentioned that on single core you had bad performance with MLIR because of FX512 and the competitors in HEXL. So my question is basically, do you vectorize in MLIR or in LLVM? And if in MLIR, at which level of MLIR?
Actually, we used both. For number theoretic transformations, such as entity, we performed vectorization. We simply used the vectorization of LLVM. But there were some cases where we needed to implement vectorization that is aware of random sampling. So for that, we implemented vectorization in the affine dialect, which is in MLIR. Does it?
Have you tried vectorizing on Lineage? Because there is a vectorizer on that as well.
Well, I haven't tried that, but it might be also a very interesting direction.
Okay, thank you.
Right. You just pass this down. Thank you.
Hi, thanks for the great talk. You showed us the poly dialect or the poly language, but obviously those are not the sort of the API of an FHE scheme, right? So how do you go from, let's say, the multiply, relinearize, etc. interface that something like here would offer to the poly dialectal language that actually corresponds to those?
Well, currently I haven't deeply thought about transformation into poly dialects, but I think it would be a definitely interesting topic. And yeah, in the future also I'd like to pursue it to that goal because it allows many interesting high-level operations, code generation of interesting high-level operations on homomorphic encryption, such as like summation of the elements in ciphertext and etc. Yes.
Any other questions? Oh, okay.
Hello, thanks for the talk. I might have a naive question, but I heard you mention complex, and you mentioned also FFT. How do you represent complex numbers in MLIR? Do you vectorize do you use vector of complex or? So that's the question. How do you represent complex numbers in MLIR? How do you vectorize the operations and things like this?
Yeah, MLIR supports complexes is a first citizen primitive type. In the first time, I concerned whether MLIR will support it well, but I found that it supports pretty well. So simply using that was enough. And well, for the vectorization, to be honest, while implementing encoding, I didn't care very much about that because most of the operations was being done on integer polynomials. So vectorizing the complex, yeah, didn't seem to have a big deal.
Okay, so you basically use the scalar complex dialect.
Yes.
And that was it. Okay. Yeah. Perfect. Thank you so much.
Any other questions? Great, let's thank our speaker again.